In this module, we are going to take the data that we simulated in our last video and see if we can write an MCMC sampler to try and estimate the model parameters and then examine whether those parameter estimates cover the true value that was used to simulate the data. So just as review, we're assuming our data come from a binomial distribution with some true number of animals n, true but unknown number of animals n. We're going to try and estimate how many animals there truly are. And there's some detection probability p. We assume that the true number of animals come from a negative binomial distribution with the expected value equal to u. And u is going to be our underlying ecological process that we represent with a partial differential equation model known as ecological diffusion. So here's this ecological diffusion model describing how u changes in space and through time. And we also have an over-dispersion parameter tau. To start off our PDE, we needed an initial condition, that is a time, what the surface looked like in the first time period. And we use a scaled Gaussian kernel where theta represents the expected number of otters in time period 1, or our very first time period, whether we call that 1 or 0. And the kappa represents the spread of that distribution. And then we can relate u here, our ecological diffusion PDE, to habitat covariates using delta, which represents our motility surface. And we want those to be positive. So we take the exponent of this to get delta by itself. And then we can use these covariates to relate motility to habitat layers. Okay, there's a little typo in here I have to get rid of, 3/7. I'm not sure where that came from. And then we have our growth rate that we add on to our ecological diffusion PDE, and we're just using a constant growth rate that's homogeneous in space. And this is analogous to exponential growth throughout our study area. And then we have priors for the parameters we're going to estimate. So what we need to do to write an MCMC for this model is to first write out the joint distribution of the parameters conditional on the data, that is the posterior distribution. And then we need to factor that into full conditional distributions for each parameter we want to estimate. And then we can sample from those full conditional distributions in our MCMC using the Metropolis-Hastings algorithm. So let's start off by writing out the joint distribution of the parameters given the data, or the posterior distribution of the parameters. And for that, I'll switch to the whiteboard. Okay, so first we're going to write out the posterior distribution that we're trying to estimate. We can start out with all of our parameters that are listed in our parameter models. Those are what we're trying to estimate. So we need to estimate the detection probability P, our coefficients in our generalized linear regression model beta, our alpha value, our growth rate, our initial conditions for u, which is kappa and theta, our over-dispersion parameter tau, and finally our estimated true abundance n. And all of this is conditional on our data at site I at time t. So this is proportional to, using Bayes' theorem of our binomial distribution. So this represents our binomial distribution for yi, multiplied by our negative binomial distribution, which is NIT conditional on, so NIT is conditional on UIT and tau. But UIT is a deterministic function of UT minus 1, delta, and gamma. So we could put in here UT minus 1, delta, and gamma. But all of these are also deterministically related to other parameters. So delta is deterministically related to beta, gamma is deterministically related to alpha, and U of t is deterministically related to U of t minus 1, and that's related to mu of t minus 2, and all the way back to u at time 1, u of t at time 1, which is in itself deterministically related to theta and kappa. So we can rewrite NIT, this negative binomial, as a probability distribution that's conditional on theta, kappa, beta, and alpha. We'll include tau here. And then we have beta, alpha, theta, and kappa. And then the rest is prior distributions. So we have our two likelihoods here. And then we have our priors for P times our prior for beta times our prior for alpha times our prior for kappa times our prior for theta and our prior for tau. All right, so that is our posterior distribution. And from our posterior distribution, we can identify our full conditional distributions for each parameter that we're going to estimate. And to identify these full conditional distributions, we just pull all of the parts within our posterior distribution that include the full conditional that we're interested in. So let's start off with the full conditional distribution of P. So this is P conditional on everything else. We can look through all of these components to identify where P is. And we see P is in our binomial distribution, and it's in the prior. So we just have two components of this full conditional distribution. And that's it. So P doesn't show up at all. There's no P in here, and then no P in any of the priors. All right, let's do beta next. Beta shows up not in here. It does show up in here, and it shows up here. Okay, that's it for beta. Next, let's do alpha. Alpha shows up here, right here, and right here. That's it for alpha. Now kappa. Many of these are going to look very similar. In fact, beta, alpha, theta, and kappa are all going to be very similar except for the prior distributions. So we can just go ahead and go through all of those. Let's do kappa. So in fact, I can just grab this component, paste it down here, paste it down here, and then just change the prior. And one more for tau. All right, the last one is n. So n shows up in here and here. And the way some people define hierarchical models is that when you have a parameter that you're estimating show up on both the right-hand side of this conditioning line and the left-hand side of this conditioning line. So because n is both on the left-hand side and the right-hand side of this conditioning line, this is a hierarchical model. So the full conditional distribution of n is going to include this part here. So we'll go to the next page and add that full conditional distribution. All right, so now we have all of our full conditional distributions for the parameters that we need to estimate in this. And from these full conditional distributions, we can develop our Metropolis Hastings samplers within a Gibbs loop, our MCMC. So let's go back to our simulated data and take a look at how that was stored, and then we can pull that simulated data into an algorithm that samples from each of these full conditional distributions using Metropolis Hastings. I recall in the last video, we had this script cotter_model_01.r, where we first developed our model that could simulate the data set from that model. And what we ended up with were Y values for our observations. What we ended up with were Y values from our observations. Let me go ahead and run through all this script again and show what our final data looked like. We have our simulated underlying ecological process U. If we plot that, we'll see this smooth process of a colonization by sea otters and how they spread out through space and time. From U, we generate the true number of animals that has stochasticity associated with it. In our ends, we can plot what that looks like. That's less of a smooth surface. It contains more statistical stochasticity involved in that. And then from our ends, we can simulate our observed data. And that includes both if we had sampled everywhere and if we had some sampling design where we couldn't sample the whole surface, we only could sample a subset of that surface. So here's that design and how that realized. And after we simulated our sample data, we need to just save a few things. We need to save our sample data that we collected, our Y values. We can save our covariate data, although we could recreate this if we wanted to, but just to save on syntax or code space on the next script, I'm just going to save this X, our covariate data, so we don't have to reproduce that. Same with our covariate data for our growth rate, although these are all just ones because we're using an intercept-only model for our growth rate. And N, the true number of animals that are out there, we don't really know what these are. So if we were using a real data set, we wouldn't have access to these N's. And that's fine. We don't expect to have access to these N's. But in terms of computation, this is a very slow sampler. If we save our N's just to give our algorithm good starting values, it'll help up with just the demonstration portion of this instead of letting this run for an order of magnitude longer to find out what the N's are. So if we can give it good starting values by using the true values, it'll save us some time in computation. When we move to the real sea otter data, we won't actually have these N's available, and we'll just have to choose something logical. For example, the N's will have to be greater than the Y's because of our binomial distribution. So we could just set all of our starting values for N's equal to something like Y plus 1. So for our simulated example, we're just going to keep track of these N's to give it a good starting value, so we don't have to do this long burn-in period. And then just for convenience, again, we're going to save our boundary layer. We could recreate this when we try and fit our model as well, but again, just to save space on code, I'm going to keep it here because we already created it. We don't need to recreate it again in the future. But again, the boundary layer is known. So I'm just, saving these 4 objects, and I'll store them in this file path called simulated data.r data, which is in the data subfolder in our sea otter materials, our sea otter folder. Okay, so I've saved those data. And everything else besides y, x, w, n in our boundary layer, we're going to get rid of. We won't need, or we'll recreate in our next stage. So let's take this information and move to our next step. We're actually going to write an MCMC model that will fit our model to these wide data. Okay, so I'm going to cancel out of this one and move over to the script called cotter_model_2. As a starting point, I'm going to remove everything. You can clear out these plots too. Again, here's what our data look like. And the way the data are going to be stored is I'm just going to I'm going to derasterize this and make just a long vector of 625 by 1 for the first time period. And then I'm going to take this one and make it into a 625 by 1 vector, and then just append it to the bottom of this one using something like cbind, or just the C function, to make one long 625 times 34 by 1 vector for our data. All right, if we were starting from scratch, we would reload in our required packages. There's a couple packages in this one that I don't believe were in the last one, chunk norm being one of them. I don't remember if MVT norm was in. I think it was, because we used the car package. Bring up those packages. I'm going to reload this calc C function here, which does our matrix multiplication. Reload our simple neighborhood function. Reload our propagator matrix function, and then load in the data. So I had stored the data, that our data file, in this file path, and I'm going to reload that in now. Okay, and from this, we're going to take our y values from that list that we created, and we're going to put them all together in a long vector, 625 times 34 by 1 vector. We have our X data that we saved from before, our covariate data on bathymetry, our vector of ones for our growth rates, and then our boundary layer. And again, I don't need this function here, but it's going to save us a bunch of time in our burn-in phase by having good starting values. So I'll just go ahead and execute that. And I'll show a script of what we would do if we were using real data, how we would choose starting values for n. All right, let's reset the study area extent to the same thing we had before, and our epicenter as the same place we had before. D is our epicenter where the invasion occurred. Choose the same discretization values that we had when we simulated our data. And then choose our MCMC settings. So let's start off with 5,000 iterations. And now I have a checkpoint, and what I'm going to do is I'm just going to save the output of this every 100 iterations in case the computer crashes or something, it doesn't finish, or I need to stop the process. It'll at least save at the last 100 observations. So I'm going to have a object called checkpoint, where later in the script it'll tell it every 100 iterations, let's save this output. All right, the next step is we want to describe our priors. So we can go back to our model. And look at our priors. Now the priors here are slightly different than the model shown here, and I can go into why they're slightly different, what we're actually going to use. For beta, we're going to use a mean of 0 and a variance of 64, or standard deviation of 8. And the reason we're doing that in this case is because we're not going to standardize our covariates. We could have standardized our covariates, but as it is, we're just going to keep them the way they are. And because our intercept we simulated it at about 15, we want the prior for beta to be able to reach 15 without it influencing it and pulling it too much towards 0. So for the sigma squared, we're going to use 8, which gives us 2 standard deviations of 16. which still puts a value of about 15 for our intercept on beta within reasonable ranges of our prior distribution for beta. For alpha, we are using 0 and 1.5 squared, just as we had in our slide here. For theta, we're using 110. I believe when we simulated the data, we simulated it from, we simulated theta from 100 instead of 500. And then with this prior here, that would make values of theta unrealistic. So we want to change the prior to give us realistic values of what the value was we used to simulate the data. We could make the variance much larger, and that would have the same effect. So a lot of options on making this prior more vague and less informed. Right here is a very informed prior, and it turns out that this informed prior is, we chose a value of theta to simulate the data that was very unlikely. So let's just rearrange that here. Kappa, I use the same thing that we used to simulate the data. We simulated the data with a kappa equal to 5, so we'll have a prior and a tight variance. We could change this. This isn't going to have a lot of effect on our results. It's very small now, so maybe I'll just make it a little bigger, so it's not, doesn't appear so informative. For P, our detection probability, we had a beta 1,1, which is equivalent to a uniform 0,1 distribution. But what we're going to use for our prior for P in this example down here is derived from this MEE paper we wrote, where we had a pilot study where we went out and photographed sea otters a number of times and tried to identify the total number of sea otters there based on replicate counts of the groups. So we used the N mixture model and estimated the posterior distribution of P from that pilot study. And that gives us information on the actual distribution of P from this study. So from that distribution, that pilot study, we obtained shape and rate parameters for our beta distribution that are equivalent to 44.05 and 13.41. So we're going to use those as an informed prior distribution on our P. Now, when we get into the actual sea otter data, we have these intensive sampling units, ISU data, and we can use that in place of this informed prior. So two options. When we're using the aerial photographs, we tend to use this informed prior here for our detection probability. And then when we use the human observations, we use the ISUs. And I'll show exactly how the ISUs fit in our model. Well, in fact, I'll talk about ISUs right now since we're talking about detection probability. When we're using the ISU data, that gives us counts of Y. So the idea behind the ISU data is the pilot flies over a transect, takes a normal count how they would, like they do everywhere else, but in a predetermined number of groups. They're going to first fly past the group, and then they're going to deviate from their route, circle back around the group, fly around them 5 times, which is roughly relates to the amount of time that is roughly the average dive duration of sea otters. And then they take a secondary count, and the secondary count is expected to be much more precise than the first count because they're able to look at the group for much longer, and the time period that they're flying around this group gives them time so that the sea otters that may have been below the surface before can rise to the surface, and they can get those unique counts. So it gives them a much more precise count, and more often, usually there's more otters in the second count when they're doing these circles around the groups than the first count. So where that gives us information, those ISUs, is it gives us information on what the N is. So at ISU units, we have data on what the true value of sea otters are, more or less. We can assume that maybe the ISUs miss one or two sea otters, but that is negligible, and that those ISU counts represent the true N. So when we have values of what the true N is and what the Y is from their first flyby of that group, then that gives us enough information to estimate P, what the detection probability is. So in our sampler, when we're using ISU data, we can plug in the plug in the ISUs here for our unknown n's and treat them actually as known, and that gives us a way to estimate P. So that's how we do that when we only use the human-based surveys. Now, when we have the aerial photograph units, we have information on P for humans, but we didn't have it for cameras. So that's why we did this pilot study where we flew over groups multiple times, taking multiple pictures, try to figure out how many there were, and estimated P using an N mixture model. And the resulting distribution was a beta distribution with these shape and rate parameters. So that's what we'll use here. All right. So, okay, and then for tau, we have 0, 100, just like we had when we showed this model. So this brings up another point, why these values are different than what I originally had in the slides. Well, it's important to note that when you're actually simulating data from a model, you choose values to simulate your data that could reasonably come from your prior distributions. And when I chose values to simulate the data, I didn't look back at the prior distributions and choose values that were within those ranges. So that led me to go back and say, okay, I chose these values to simulate data. I should have looked at these prior distributions earlier to see if they're reasonable. I didn't, so now I have to change the priors. Or I could just go back and resimulate the data using values that were in here. Either one would be fine. All right, so I have all of our prior this information here that I'm putting in are also called hyperparameters. They're the parameters of the prior distributions. I have all those in. Now I need to choose starting values. To speed up convergence, I'm just going to choose starting values that are equivalent to the true values. If I really wanted to test this model, I would deviate these a bit and made sure they converge down to the true values. But I've worked with this model enough to know that they in fact do. So to speed up convergence, I'm going to choose starting values equal to the true values, and we'll see what those behaviors look like. I also need to run these deterministic functions to get the starting values for delta, which depend on beta. Gamma is going to depend on alpha. I need to describe a neighborhood matrix. I only have to do this step once. I don't have to do this each time within the MCMC iterations because the neighbors are always going to stay the same. So I need to calculate this H matrix that depends on delta, which in turn depends on beta, and then H depends on gamma, which in turn depends on alpha. Remember, I want to make range between 0 and it can be greater than 1. So if it's greater than 1, it indicates that the population is growing. So that's the alpha value, the growth rate. The population is actually growing within the cells, but it can't be less than 0. Okay, now I need to set my initial condition, U0, which depends on kappa and theta. These lines, I'm just going to create an empty raster. I need a distance matrix for all of my points, how far they are away from our epicenter D, which is right here. And then I can calculate mu0 using this kernel of the normal distribution, which depends on kappa and theta. All right, I'm going to create an empty raster brick to store all of our U values through time. And here is the computationally intensive step, calculating U from our starting values. So we're starting off with U0 at time period U. So that's this part right here. And then we're propagating this forward for all of our time periods using this function here, which depends on the H matrix. And this step takes a second. So that took a few seconds calculating that. Now by itself, calculating that once is not a big deal, but we're going to have to calculate this several times within a single MCMC iteration. So if I go back to our full conditional distributions here, we're going to have to calculate U every time we need this negative binomial distribution because U is going to show up in here. So whenever this shows up in our full conditional distributions, we're going to need to do this function. So it shows up 1, 2, 3, 4, 5, 6 times because it shows up here. So within one MCMC iteration, we're going to have to calculate this function 6 times. And you can see about 3 seconds to calculate it once, times that by 6 is 18 seconds. 18 seconds for one MCMC iteration. If we have to do 5,000 MCMC iterations, then it starts to become a computational burden. And we'll see how long this takes. Then we create our U. Like our Y values, we're going to stack all of our U values into a single vector that's 640 times 34 by 1. All right, now, if we didn't have good starting values for n, we saved our true values of n from our simulated data so that we could give it good starting values. But if we didn't, one thing we can do is simulate them from our starting values from U with some checks on it. So we could just simulate n using a negative binomial distribution that depends on our starting values of U and our starting values of tau. And that'll give us a reasonable starting place, but we still need some checks. And that check is, because we're using a binomial distribution, we need n to be equal to or greater than the observed data y. And when we do this step here on line 252, that doesn't guarantee that n will be greater than or equal to y. So we'll have to change those starting values. We can use an if-else statement and say, if n is less than y, which it can't be, it'll give us a computational error. Then let's just change n to our y values. But if n is not less than y, let's just use the n we sampled using the negative binomial distribution. The other thing we want to do is, well, we really only need to make these checks where we actually observe data. So we're going to have n everywhere in our study area, but y is only going to occur where we actually sampled the data. So that's why we have this sampled and not sampled line here on 253 and 254. So we can align our n's and our y's only at the sampled areas. So we could use this as our starting values, and that would be fine. It would just take longer to burn in for n's to converge to their true values. Instead, we're going to use the n's that we saved from our simulated data just to speed up convergence. All right, in our MCMC algorithm, we are going to sample from our full conditional distributions, and we want to store those samples for the end. So I'm just going to do a bunch of bookkeeping here that stores all of our, that creates matrices to store all of the samples we pull from our full conditional distribution. And I'm going to tell it where I want to save results on our checkpoint. Now, there's lots of ways to do this, to store values. This is one way that I chose here. Create a list and then store all of our sample values in our list. So we're going to store all of our sampled alpha values. We're also going to need a tuning parameter for alpha. We're going to store our beta values, our theta values, kappa, p, tau. We're going to look at total population size everywhere in the study area as a derived parameter. Basically, we just add up all the n's in our study area for each time period to see how that changes through time. So the marginal population size, marginalizing over space. And then we want to store our tuning parameters so we can modify those later if our model hasn't yet been tuned, and our storing location. Okay, so we need to choose some tuning parameters because we're using Metropolis-Hastings, which requires tuning. None of these are conjugate distributions because of that log transformation in delta. Let's see, if we had p, binomial beta, actually p is conjugate. So we don't necessarily need to tune p. We have a binomial and a beta over here. We have a binomial distribution and a beta distribution. So that's actually conjugate, and the resulting posterior distribution is a beta distribution with something like number of successes as the shape and the number of failures as the rate parameter plus our alpha, our shape and rate parameter for our prior distribution. But the other ones, because of the log transformation in the betas to the negative binomial, they are not conjugate, and we're going to have to tune a Metropolis-Hastings algorithm. So these are the tuning parameters. As you can see, these are very specific, and that's because I've already tuned this model. I ran it through 5,000 iterations with much less specific tuning parameters. I think I set them all at 0.01 to start off, and let it auto tune, which I'll show later, the auto tuning process, until it finds the very good tuning parameters where we get about 40% acceptance rate in our Metropolis-Hastings algorithm. Along with our tuning parameters, we need acceptance ratios. Again, we want to achieve about 40% acceptance rates. Okay, so that's all of our bookkeeping before our Gibbs loop. So we set everything up, and now we need to develop our Metropolis-Hastings samplers for our full conditional distributions. So using our Metropolis-Hastings algorithm, we have to look at our full conditional distribution for each of the parameters we're sampling. So here we'll start off with P, and P includes a binomial distribution and a beta distribution. So we see in the numerator in our Metropolis-Hastings ratio, we have the binomial distribution, and this includes for all I equals 1 to n and all t equals 1 to t. That's this sum function. We're summing up over all of those. Here we have the product, but we're taking the log of these values, so we can use the addition. That's why we have our sum of our y sampled sites and our n at those sampled sites, and then our proposal for our p-value. So I'm not going to go fully into Metropolis-Hastings ratios here. There's a lot of good information on how to use Metropolis-Hastings, but it includes our proposal distribution, which we're using a truncated normal for P, because we can tune this and we can also keep it between 0 and 1. We have our two components of our likelihood, including our Y, and then our prior distribution, which is beta. And then we have our offset for our asymmetric proposal distribution. So a truncated normal is an asymmetric distribution because it's truncated at two sides, and the mean is not necessarily 0.5. So we need to incorporate that offset into our Metropolis-Hastings ratio. The numerator includes our proposed value, and the denominator includes our original value of P. So we have P in the bottom and P star in the top, and we want to see which one is better. So we have MH1, MH2, and then we compare that on the log scale here. So we exponentiate it back to get our Metropolis-Hastings ratio. If Metropolis-Hastings ratio is close to 1, then we're going to accept it with probability equal to a uniform distribution between 0 and 1. So if MH is greater than this value, we're going to accept our proposed value. If it's less than this value, we're going to keep our original value and just skip this whole step. And then we move on to the next parameter. All right, so I mentioned that P was also conjugate, so we have Metropolis-Hastings here, but we could do just sample directly from the posterior distribution using the conjugate beta distribution. So P could equal our beta. We'll take one sample, and the shape is going to equal the shape is going to equal our prior value for our shape. So P dot shape plus the number of successes, which would be the sum of Y sampled. We will need to remove NAs here. We could just remove all our unsampled areas. And then the rate is going to equal our rate from our prior plus, okay, and so there we have our conjugate value for P. And we can use that because it'll be faster than a Metropolis Hastings ratio by about 60% because we are going to accept all of our draws. So we have a very nice proposal distribution, which is equal to the posterior distribution. So we don't need to reject any samples. All right, next is sampling beta. So we can use, for sampling beta, we're going to use a block sampler. We're going to sample all 5 of our betas at the same time. We'll use a multivariate normal distribution to sample one value that includes our prior values of beta as our mean, and then our tuning parameter is centered on this beta tune. But again, I mentioned we didn't scale our parameters for beta. We're keeping them in their original units. So to allow the tuning parameter to affect the values of beta, the proposal values of beta differently, we're going to use the variance, the estimated variance based on our x's, our covariate values, to offset that sampler. So we have x transpose x inverse times sigma squared, where in this case sigma squared is our tuning parameter. And that'll allow our betas to tune more efficiently since we didn't scale them using Z standardization. Once we have our betas, we can calculate all the other deterministic functions that depend on beta that also change when we change beta. So that includes delta. And then once delta changes, we have to recalculate H. All the other values in H stay the same. So gamma stays the same in calculating H, but delta is going to change. So we have to change H. And then if we have this condition in here, that if H is less than 0, we're going to skip this. So if we propose values of beta that result in our H matrix becoming less than 0, then we're just going to skip this entire step, because if it does, it's going to lead into our sampler or our numerical approximation failing and leading to chaos. So we're only going to evaluate proposed values when they make sense. So after we calculate H, we can recalculate U, and then this again is our computationally intensive step. And then we align U to align with our data, and then we have our Metropolis Hastings algorithm again. Alpha is very similar. We only have one value of alpha, so we can sample just from a univariate normal distribution centered on its previous value, and then with tuning parameter alpha. Again, when we change alpha, we have to change H, and when we change H, we have to change U. So we have different proposed values for U, and then we compare those in our 2 likelihoods from our full conditional distribution from beta for alpha. So again, we have our negative binomial distribution here, and then alpha has a normal prior. So we have our negative binomial distribution here and our normal prior. I skipped over alpha, beta, but it's very similar. We have our negative binomial here and our normal prior with our hyperparameters in our prior distribution. Kappa, very similar. We propose a new value of kappa. This is a truncated normal. The only difference between alpha and beta and kappa now is we have to include this offset for the asymmetry, because we're using an asymmetric prior distribution. Also, we're truncating kappa between 0 to be greater than 0. So we're using a truncated normal here as well. So we have 2 truncated normal distributions in our Metropolis Hastings numerator and denominator. One is because our proposal distribution is asymmetric. So that's our offset for our asymmetric proposal distribution. The other one is because our prior is asymmetric. So if we go back to our model here, kappa has 0 truncated normal prior distribution. So we have to include that trunk norm here. All right, same thing with theta. The one thing about kappa and theta is they affect the initial condition. So when we propose a new value for kappa, we also have to propose a new initial condition because that's deterministically related to kappa and theta. So we have theta here, and theta stays the same in our full conditional for kappa, but kappa is different. So we recalculate U0, and then we start all these over with U0 dot star here. All right, similar for theta. Okay, for tau, we are going to use a uniform distribution between 0 and something very large. Remember, as tau gets large, it approximates a Poisson distribution. So we'll just let this be very large and 0 between 0 and whatever. So we can tune this truncated normal distribution. But then when we tune it, we have to account for the asymmetry in this distribution. Now, tau officially has a uniform 0, 100 distribution. As long as these values stay between 0 and 100, we don't need to include it because every value between 0 and 100 is equally likely. We could put a constraint in here to make sure we're only sampling from values between 0 and 100. So if tau dot star is greater than 0 and tau dot star is less than 100, then we'll go ahead and do all these steps. So that will fully incorporate our prior distribution in here. All right, and then the last full conditional distribution we have is n. N is an integer value, and sampling integers are more complicated, or are less easier to tune. They're harder to tune than continuous variables. So when we sample integers, I could do a block sample and sample all the n's at the same time, but there's a lot of n's. There are 625 times 34 values of n, so 21,251 values of n. And when we sample all of these at the same time, using this method here, our tuning parameter is going to have to be very small. It turns out we're going to reject the samples a lot. We're not going to get that 40% accept reject rate, ratio that we like. The rejection ratio goes way down. So instead, what we can do is sample all of our n's and compare them individually, but also simultaneously. So I'm going to sample new values of n by using the old value of n and just adding 1, 0, or -1 to that value. So it's not really, we could tune this by making this range from -2 to 2 or whatever, but it turns out that smaller increments are better for convergence. So we're going to add either -1, 0, or 1 to our n value. And then if our n is less than 0, we're going to just give it the old value of n, because n has to be greater than 0. So if it's less than 0, meaning it went from 0 to -1, then we're going to say that n equals 0. But if n is less than y, we're going to say that n equals y. Otherwise, we're going to say it equals our new proposed value of n. So it meets these constraints that n has to be greater than y, but n also has to be greater than 0. So we can sample those, and then we can compare, use the Metropolis-Hastings ratio to compare new proposed values of n to our old values of n in both our binomial distribution and our negative binomial distribution. Now, because y is only sampled in certain places, this is going to give us a lot of NA values, because when y comes in this binomial distribution and it equals NA, we're just going to get NA returned from here for both MH1 and MH2. But we can reject all of the new NHs, all the N's. We can reject all of the N's where it is NA by using previous values of N. So we have an additional step in sampling N here. And then when we actually look at our sampled values of n's, we have values everywhere. All right, so those are all of our full conditional distributions. We use Metropolis Hastings on all of these by taking this information, except for P, which is conjugate. We developed our MCMC from those Metropolis Hastings ratios, and all is left is to save the results, set up some auto tuning, and calculate our derived parameters. We can calculate a total population size in each time period by using this this function here, sequence along, where we're going to look at our vector for n, and for every q value, for 1 to every q, we're going to just sum up those values. And that'll give us our total population size in a vector, and we can store that. That's just a derived parameter, so we can do that using equivariance property of MCMC. Then we can store all of our values we sample from our full conditional distributions. We're also going to want to store our tuning parameters. Because this is Metropolis Hastings, we're going to have to tune these parameters and then evaluate them after we are tuning them. So how do we tune our parameters? We can use, there's more sophisticated methods than this, but this one's easy for me to remember and easy for me to code. So if the acceptance ratio divided by the iteration we're on is less than 30%, meaning we're rejecting more than 70% of our samples, let's make our tuning parameter smaller. So let's say alpha tune equals alpha tune times 0.9. On the other hand, if our acceptance ratio divided by the number of iteration we're on is greater than 50%, meaning it's too high, we're accepting parameters too often, let's increase our tuning value by multiplying it by 1.1. And then we can do this for all of our parameters in turn, and then we can save all of our output. Now here's our checkpoint. So if this condition is met, so every 100 iterations, this is going to be true, then we're going to save our output. And that way we can view our output even before our MCMC finishes. We can see how it's doing, if it's getting stuck, if we drastically need to change our tuning parameters. Then we'll keep track of what iteration we're on and then calculate how long it took. So this is going to be slow. We've got 5,000 iterations. I'm going to go ahead and run this entire algorithm, and then we'll come back and take a look at the results when it finishes. Okay, so we're back now. We've given this a day to run. We can look and see that it took about 1.07 days to complete our 5,000 iterations. And again, our goal is to examine whether the approximated marginal posterior distributions of all of our parameters cover the true values that we use to simulate the data. So we'll just scroll through all of our trace plots, plot those along with the line that shows the true values, and examine whether they include the marginal posterior distributions include the true values. All right, so first let's look at our detection probability P. You can look at the trace plot there, and we see that we probably want to give this some more chains, maybe 10,000 iterations, and maybe thin it by 10. But on average, we have the marginal posterior distribution covers that true value. And we could examine this for another 2 days if we want and let it run for 10,000 iterations to see how that looks. All right, in terms of our betas, we have our intercept. Our intercept does a good job recovering that true value. Beta 1 covers that true value. Beta 2 covers the true value. Beta 3 covers the true value, and so does beta 4. We can do a couple more things to further assess these. We could plot the actual densities of the marginal distributions. So if I do plot density of beta 1, and then look at a vertical line and see where that vertical line is in our density, and we see that it's near one of the modes there for beta 1. We could do a similar thing for the other betas. And recall these marginal posterior distributions, or approximations of marginal posterior distributions, describe our relative degree of belief of what that true parameter is, conditional on everything else. So conditional on the uncertainty in all of our other parameters as well. And we can see for the most part that we have a high relative degree of belief of where that true value is. All right, we could continue to do that. The other thing we could look at to see whether or not the true value is within the 95% credible interval is look at the quantiles of our betas. This one was close, but we can examine the quantile of this and see if the 95% credible interval covers that true value. So we could put our lines at those values, negative 0.42 and 1.20. And the true value is 1.03 here. So we see that our true value is within the 95% credible interval. And if we repeated this simulation a large number of times, we would expect on average that 95% of the time, our true value is within the 95% credible interval. That's kind of blending frequentist approaches and Bayesian approaches. And there's a good discussion on this type of approach in a paper by Little in 2006 in the Journal of Statistical Science. And it's titled something along the lines of calibrated Bayes. And it talks about using these ideas of simulated data with true parameter values and examining how many of the 95% credible intervals of the marginal and posterior distributions cover the true values to simulate the data. All right, let's continue on with alpha. Alpha is our growth rate. We can see our our estimated growth rate is right in the middle of what the true value was. We can plot the density of that. And we see we hit it about perfectly there with the mode of our posterior distribution. Kappa for our initial condition, again, very good. The expected number of sea otters at the epicenter in the very first time period, again, very good. Our over-dispersion parameter, very good. And then we can plot the mean process, what that underlying process U looks like that we were trying to estimate. So if we take the posterior mean of all of our parameters and use those values to calculate U through time, we can get what the expected value of that process looks like based on the posterior means of each of our parameter values. And here is our estimated process. Now we could go back to our previous video. I'll insert a clip here following this to compare our estimated process compared to the true process. The other thing we can do is look at uncertainty around this process. So this is the expected process using the posterior means, but we could also look at what the 95% credible intervals of this process are. So if instead of using the mean of all these values, we take the quantiles for our lower bounds and our upper bounds. Let's start off with our lower bounds. And we can look at the credible intervals of this process for the lower bound. Oh, it looks very similar. Let's go back one. You can see a little bit of changes down here, but otherwise virtually indistinguishable. There's the lower bound on the quantile. There's the estimated mean. And if we want, we can change this from our lower bound to our upper bound. So here we have the mean estimated process, lower bound on our process, and then the upper bound on our process. Okay, so what we have done so far is we have developed a model to describe the spread of organisms through space and time using a PDE. We developed a model to simulate data from that PDE. And then we actually simulated some data using that PDE, and we tried to recover the parameter values that we use for simulating the data using an MCMC. We fit our model to our simulated data, and we discovered that we can recover those true parameter values using our MCMC. So our next step is to not use simulated data, but to try and fit this model to the real sea otter data to try and understand what this underlying process is of sea otter spreading throughout anywhere, whether it be Glacier Bay National Park or Katmai National Park or off the coast of Washington. So that'll be the focus of our next module.